Welcome to EPG Pathshala. Today's module is about the applications of solar energy. We all know in the sun, solar energy is produced by the nuclear fusion reactions. And this incident solar energy is generally transformed into thermal or electric energy using various devices. But the incident solar energy is not fully utilized for meeting the energy demands at the same time of this insolation. The solar energy is, however, available during the sunshine hours, and the demand of thermal or electric energy may not exist during the non-sunshine hours. And also, the maximum availability of solar energy may not coincide exactly with the demand of thermal or electric energy. So, the availability of solar energy sometimes are low for several days due to cloudy days, resulting in the substantial lowering of its output to the thermal and electric energy. So, it requires storage for further applications. In this module, we are going to discuss about what are the different solar storage systems, what are the applications of solar energy, especially with respect to the thermal applications, how the active and passive solar heating differ, and also the electrical applications. It is essential to store energy output, whether it is thermal output or electrical, from the solar devices during high insolation, that is incident solar radiation, from the solar device during the time when it received to meet the thermal and electric load demand during peak demand time. During low insolation time, solar energy storage system enables delivery of more power than what is generated by the solar, electric or thermal plant. And so it enables to match the generation of energy with its load demand. There are different types of solar energy storage system. It can be classified as thermal energy storage system, electrical energy storage system, hydrogen energy storage system, electromagnetic energy storage system, and biological storage system. Thermal energy storage system. The thermal acid batteries are the most commonly used means in chemical energy storage system. The advantages of this storage are good working efficiency up to 80%, low cost, rapid change from charging to discharging mode, and slow discharge rate. A storage battery takes electrical energy generated by solar radiation and stores it as chemical energy. It later supplies electric energy by converting this stored energy. Electrical energy storage. A capacitor is used to store electrical energy in electrostatic field when it is charged. The capacitor of large capacity is required to store a significant amount of energy. Hydrogen energy storage. The electrical energy is used to decompose water or splitting the water by the electrolysis reaction into hydrogen and oxygen. These substances can be combined to release the stored energy when required. Electromagnetic energy storage. The electrical energy is used to store energy in a magnetic field. The resistance of the coil wire is made almost negligible so that the stored energy in the coil is not dissipated out, and stored energy in the magnetic field can be maintained indefinitely. The electromagnetic energy storage requires the use of superconducting materials. These materials develop almost zero resistance to electricity flow when cooled below a critical or transition temperature. This method of storing electromagnetic energy is also known as superconducting magnetic energy storage. And the electric energy can be recovered when the coil is discharged. Biological storage, it refers that the solar energy is stored in plant by the process of photosynthesis. It's the process in which organic compounds are formed in the green plants or the green algae using carbon from the atmospheric carbon dioxide in the presence of sunlight. The plants on decaying from this biomass can be converted into various types of solid, liquid and gaseous fuels. Sensible heat storage. The thermal energy is stored in this type of storage by virtue of heat capacity and temperature difference developed during charging and discharging. The temperature of the storage material rises when thermal energy is absorbed and temperature drops when thermal energy is taken out. In this storage, the charging and discharging can be performed reversibly from an unlimited number of times. The sensible heat storage can be of liquid media storage or the solid media storage. We will see the sensible storage of the heat by the water. Water is considered as the most suitable media for the storage below 100 degrees Celsius. Liquids such as oil, liquid metals and molten salt can also be used as liquid media storage. The water thermal energy storage can be short-term and long-term. A short-term storage system has a well-insulated storage tank as shown in this figure. The storage in such a tank is very economical for a few days only, as the heat is lost over long duration, making the storage uneconomical. Long-term sensible heat storage by this water is possible in underground reservoir having a special insulation. In this system, water is heated in charging mode by passing it through a heat exchanger and then it is stored in an underground reservoir. In the discharge mode, the hot water is made to flow back through the heat exchanger where it releases the stored energy as shown in this figure, but with the reverse circulation. And the advantages of this storage system are abundantly available, inexpensive, high specific heat which enables to store more heat per unit mass, low viscosity requiring less energy to pump through the pipe system, can be used for both storage and working medium, and is stable with no harmful effect. But disadvantages are it has limited temperature range of 0 to 100 degrees Celsius, it results in corrosion of pipes and can leak easily as it has less surface tension. Solid media storage or packed media storage. This type of storage has a bed loosely packed solid materials such as rocks, sand, concrete, pebbles and metals to store sensible heat. A fluid such as air is circulated through the bed to remove the heat from the storage. This type of solid media storage has no limitation such as the low temperature due to freezing and high temperature due to vaporizing, as it is applicable in the case of liquid media storage. So, it is better than the liquid media storage. A typical packed bed storage unit is shown in this figure. It consists of a container, a screen to support the bed, inlet duct and the outlet duct. The advantages of this solid media storage are the stones or pebbles are abundantly available, low cost, non-combustible, easy to handle, the possibility of high storage temperature, no freezing point during the heat removal, no corrosion problem, no requirement of a heat exchanger, but it has disadvantages like the size of the storage container is large, simultaneously charging and discharging of energy is impossible in this media, large pressure drop needs high temperature or high capacity air blower. Latent heat storage. In this storage, heat energy is stored by virtue of latent heat, which is required to bring about phase change of storage medium. The heat required to bring about phase change of a material is much larger compared to the sensible heat change of the same material. The phase change of a material also involves absorption or release of large quantity of heat energy at a constant temperature, which is impossible in the case of the sensible heating. Therefore, latent heat storage system is more compact for a certain heat storage compared to sensible heat storage. The phase change which can be used for storage system are solid-solid, solid gas, solid liquid and liquid gas. Solid gas and liquid gas transformation involve large volume changes, thereby making this system impractical and most complex. But solid-solid transition involve transformation of the material from one crystalline form to another, thereby resulting in the transformation with small volume changes. Hence, such storage systems are practical and preferred in spite of small changes in latent heat possible during this transformation. For the phase change storage media, salt hydrates called global salt, that is Na2SO4 10H2O, these are preferred. These have solid liquid transformation. Besides these hydrates, paraffins and non-paraffins like ester, fatty acid, alcohol and glycols are used for this storage. The hydrate crystal have water of crystallization and can be represented as XYN MH2O. That is, one atom of X, N atom of Y and M molecules of water in one crystal. When the hydrate crystal are heated to transition temperature, These crystals release their water crystallization and anhydrous salt, that is hydrates without any water, get dissolved in the released water. But the problems faced with the use of the salt hydrate for the latent heat storage are: released water crystallization is insufficient to dissolve all the solid salt produced on heating. The anhydrous salt settles down at the bottom of container. The recrystallization becomes impossible on removal of heat. The process becomes irreversible and performance degradation takes place. Mechanical means vibration or stirring. The suspension media or thickening agents have to be used to make the system work in reversible manner without performance degradation. And this problem can also be resolved by limiting the vertical height of the container. And also the heat of fusion is small in this type of storage. Now coming to the applications of solar energy. The application include solar water heater, solar pond, solar thermal pump, solar furnace, solar heating, active as well as passive, solar cooker, solar passive space cooling, distillation and electricity production by the photovoltaic technology. The solar water heater. A small capacity water heating system with natural circulation is shown in this figure. It is suitable to supply hot water for domestic purposes. It has two main components which include flat plate collector to convert solar radiation into heat energy, water storage tank to store hot water. The tank is located above the level of collector. The natural circulation of water is established from the collector to water tank and then from water tank to the collector. The hot water for use is withdrawn from the top of the tank, which is replaced by the cold water entering at the bottom of the tank. The water heating system is also provided with an auxiliary heating system so that the system can also work during cloudy and rainy days when sufficient solar radiation is unavailable. Solar pond. In ordinary ponds, when water is heated up by the sun rays, the heated water rises to the top of the pond. The hot water loses heat to the atmosphere, and so the net temperature at the top of the pond remains nearly at atmospheric temperature. The solar pond technology ensures that heated brine water remains at the bottom of the pond due to more brine concentration and density in it. The solar pond serves the dual purposes of a large flat collector and a thermal storage system. It consists of a large size brine pond, depth of about 1 meter, which has a salt concentration gradient in such a way that the most concentrated and dense part of the brine solution is at the bottom of the pond, and brine concentration gradually reduces from the bottom to the top of the pond based on the variation of brine solution density. A solar pond has 3 zones. The top zone is the surface zone, which has least salt content and its temperature is the atmospheric temperature. The bottom zone collects and stores the solar energy as heat energy. In between these two zones, there is the gradient non-convective zones. The hot brine solution from the bottom of solar pond is taken out without disturbing the brine gradient existing in the solar pond. This solution is taken to heat exchanger to remove used to run the turbine, which is coupled to a generator to generate the power. The refrigerant vapors existing from the outlet of the turbine are condensed to liquid state in a condenser and pumped to heat exchanger. The solar pond electric power plant is given in this figure. Solar thermal pump. Solar pumping utilizes the mechanical power generated by the solar radiation to run the water pump. Solar energy offers several beneficial features which makes it utilization in the irrigation pumping. The features like need of the pumping arises most during the summer months when solar radiation is intense. Pumping can be carried out intermittently without any problem. Surplus pumped water can be stored in a reservoir or the tank. The requirement of water decreases during period of low radiation when solar pumping decreases. Evaporation losses reduce during cloudy days. Rainwater is also available during the rainy days. There is relatively inexpensive running and maintenance cost. The solar pump is similar to solar heat engine working in low temperature range. The source of heat engine works in low temperature range. The source of heat is a solar heater. The heat is transported to a heat exchanger where heat is transferred to a refrigerant of low boiling point. The refrigerant evaporates and high pressure vapor is taken to a turbine to do the mechanical work by running the solar pump. It is shown in this figure. The outlet refrigerant vapor from the turbine is condensed and takes to heat exchanger using feed for the reuse. Solar furnace is used to study the properties of the material such as physical, chemical, mechanical and electrical properties at high temperature. The focusing type solar collectors can concentrate solar radiation over a small area in a furnace for heating of materials. It is possible to obtain high temperatures which can be about 3500 degrees Celsius. The solar furnace has two main components, a concentrator with arrangement to position these materials in focus and a system of large number of small heliostats. The large number of heliostats are located and positioned in such a manner that they direct solar radiation paraboloidal collector as given in this figure. The solar radiation after reflection from the heliostats moves parallel to the optical axis concentrator. The heliostats are provided with a system of sun tracking. The concentrator focuses incoming solar rays on the test material to heat up. The solar furnace is mainly used during the sunshine hours. Here the cost of equipment is very high and the material with small area can only be heated and tested. These are the limitation of the solar furnace. The major application of solar energy is the solar heating. Can be passive or active solar heating. Passive solar heating is a method of heating with solar energy that does not require mechanical power to circulate heat. Instead, structural designs are used that help to absorb solar energy and allow the heat to circulate by natural convection. Active solar heating is a method of heating with solar energy that requires mechanical power such as pumps and fans to circulate the heat from the solar collector. The solar collector collects the solar radiation, tubes filled with liquid lie on the metal plate are heated up. This is connected to pipes that carry the liquid through a building. A pump moves heated liquid through a pipe which runs through the heat exchanger and heat from the hot fluid in the pipe is transferred to the water. The heated air transfers heat throughout the room by convection. The cooler water in the pipe is then pumped back to the collector where it is reheated. The hot water in the heat exchanger is transferred to a storage tank for later use and cooler water is pumped into the exchanger to be heated. Solar passive heating. Solar energy can be used for the passive heating of building to maintain comfortable temperature inside the buildings. Passive heating of building does not require any mechanical device. This heating consists of natural processes such as convection, radiation and conduction design to ensure natural flow of heat in the space inside the building. Such specially designed building is called solar house. In the northern hemisphere, the sun rays come from south direction. Hence, in order to achieve solar passive heating in cold regions, south facing wall is made thick using concrete or stone to store the maximum heat energy from the incident solar radiation. The entire south wall is further provided with a plastic or glass sheet covering with an air gap in between the wall and the sheet covering. The incident solar radiation after passing through the sheet covering is absorbed by thermal storage wall. The warm air in air gap rises and enters into the space from the upper inlet vents and cold air is removed from the space from the lower outlet vent. This is shown in the figure. Solar passive space heating. These systems capture the sun's energy to supplement the existing heating system for a home or commercial building. The heating system intensifies the sun's power to heat water or the air that is then used to heat the building. Solar passive space cooling. Direct sunlight heat which can be reduced by using the shading and providing Venetian blinds to glass windows and doors. Conduction of heat through the walls, roof and the floor. It can be reduced by providing the insulation. The maximum heat is conducted through the exposed roof which has to be provided a false ceiling with a good insulating material to reduce the conduction of heat from it. Infiltration of outside hot air. It can also be reduced by the proper sealing of the space and reducing the opening of doors and windows. The methods to reduce or prevent heating of the space are shading of glass area and the walls, providing air circulation or ventilation so that warm air is driven out, cool air from the outside is sucked into the space using chimney effect as given in this figure, providing a pond on the roof to reduce radiation heating and achieve cooling below the pond. Providing black plastic bags on a metallic roof which helps in radiating out the heat from the space during night time. Providing ground coupling or basement construction to maintain temperature of the space close to ground temperature. Another application is solar refrigeration and cooling system. A simple solar operated absorption refrigeration system to cool a space is given in this figure. The hot water transported from a flat plate collector is passed through a generator which is heat exchanger. The heat is transferred to a refrigerant and absorber solution. The refrigerant can be an ammonia or water, while absorber is water or lithium bromide that generates refrigerant vapors at high pressure vapors which are condensed to high pressure liquid in the condenser. The high pressure refrigerant liquid is throttled to low pressure and temperature by an expansion valve. The low pressure refrigerant takes heat from the evaporator and vaporizes, thereby cooling air or water which can be used for cooling the space inside the building. Another application is solar cooker. A solar cooker consists of an insulated box of blackened aluminum in which utensils with food materials are kept and reflector mirror hinged to one side of the box so that angle of reflector is adjusted a glass layers consisting of 2 layers of clear window glass sheets. The box is kept in such a way that solar radiation falls directly on the glass cover. The reflector mirror is adjusted in that way. Additional solar radiation after mirror reflection is also incident on glass cover. The glass cover traps heat owing to greenhouse effect, providing more heating effect. The air temperature inside the box ranges from 140 to 160 degrees Celsius, that is enough for the boiling and heating purposes.